who cares what the medium is, right?
You can't call it a photo. You can't call it a photograph. That's all. So people, yeah.
Had this battle at Astronomical Society of South Africa. They kept telling me to rename the section, and I stood my ground, and eventually I just gave up fighting. So.
Well, when I was saying like the first photograph of a black hole, right, when we had the Event Horizon telescope picture, and everyone was like, it's not a photograph. And I'm like, well, it's photons that have been rendered. Well, then what is a photo? Is when you take a picture with your phone, is that a photograph?
You have to use the emulsion on a plate, apparently.
Yeah, exactly. You have to use a chemical emulsion to take a photograph. Anything else is completely, an irresponsible use of the language. This is an
official clash of cultures right now.
Oh, we're live, by the way.
Yeah.
Yeah.
Just in case. Just in case everybody was wondering where.
Thanks for that.
Yeah, we're live. But yeah, so I don't care. You know what? Talk to my boss. Oh, it's me. So,
wow, way to rub that in. Yeah. Good job.
There are a few downsides to being entirely responsible for everything that goes on within your organization. But one of the upsides
is really nice to have people who are actually in charge of making decisions, and it's not.
Yeah.
Really nice.
The rough part is when you're both in charge and you do most of the work. That's when it gets a little tough. Hey everyone, welcome back to the Weekly Space Hangout. And now you've all had a chance to say hello, and so I'm going to say hello back to Alex Displan, Ben Kalo, Bob Moeller, Christian Woodland, David Dunn, Eric Schneider, Grant Lanning, Ian Farquharon, Janelle Duncan, Johnny J, Jorn Albert, Luke Duke, Nancy Graziano, Paranor, PsychoCat749, Rich Wilson, Arjone, Scott Bragdon, Sephirin, Sergio Botero, Susan Murph, Von Lichtenbutts, Yamagashi-san, and Zappan. Hey, everybody. What else is happening? Well, we kill one more minute.
No? Between the upcoming AGU conference and the upcoming holiday, that's like literally all of my time.
So we were talking about before we actually started here, how weird it is that Black Friday is coming up this weekend for everybody in this thing except for you, Kimberly.
Well, I mean, there is Black Friday here in Washington, D.C. as well.
Yeah.
I just refused to participate because I was traumatized as a kid for like being dragged to all the stores at whatever o'clock it was.
But here, let's just for the participants here, show of hands, everybody who has Thanksgiving in November.
Hi. It's me, the only person here in the U.S.
and yet, okay, and everybody who has Black Friday sales on Friday.
It's America's gift to the world.
This is what you've done to us.
Day of excessive consumerism. You're welcome.
Thank you. We appreciate it. And we're gonna.
But I like these sales, like €1 discount. And they are saying, oh, it's 50% discounts, but then when you check the prices, it's totally not.
Yeah, there was some recent thing like of the advertised Black Friday sales, there's only like some very small percentage that are actually a decent discount for the day. It's just like it's all gimmicks to get you in the store. Yeah. I'm like, why would I do that? I hate going to stores anyway.
Oh, the week before they go down with the price, and then on the Black Friday they come up, or vice versa. The week before they they go up with the prices, and on Friday they go down.
It's like, oh yeah, we totally marked that down from our inflated price.
All right. It's time. It's happening. All right. Just gonna chip back to the screen. There's me. Here's my intro. Here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, November 27th. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about planets around a supermassive black hole. Borissov getting close to Earth. Black holes triggering star formation. And Nika, you're going to have to help me out here. Space 19 Plus ESA Budget Council for the ESA Council at ministerial level. I have no idea what that is, but I'm intrigued.
I will talk more about it.
That sounds good. Joining me this week on my screen right now, Nika Klimuch from Germany. Nika.
Hey. Hello, space enthusiasts.
As always, good morning.
Good morning.
Actually, we're really covering almost all the time zones here. So from South Africa, we got Alan Versfeld. Alan.
Hey, yeah, these time zones messed me up. I got here an hour early and then almost fell asleep at my desk. So it's 3 a.m. now, yeah.
From, oh man, crazy. I have no idea why you guys are willing to do this, but I appreciate your enthusiasm. From the East Coast of the United States, Dr. Kimberly Cartier. Kimberly.
Hello, happy podcast day. And yes, the East Coast of the US. You're right.
And of course, I'm on the West Coast of North America. So I think we cover many of the time zones, and we're going to add one more in a second here. But before we do, I want to give a big shout out, of course, to our good friends at the Weekly Space Hangout crew. They are the executive producers of this show. I am not kidding. They organize the guests. Anyone who joins this community instantly becomes an executive producer and then has all the power and clout to boss me around, boss the rest of the co-hosts around, and summon any guest you want. Go ahead. We support it. We can't wait. So if you want to be a part of this amazing community, go to wshcrew.space. They'll hook you up. They'll put you in charge of me, and you're going to have a lot of fun with a great community of people. wshcrew.space. All right, let's get on with this week's guest, adding another time zone. We've got Dylan O'Donnell from Australia. Dylan.
Hello, Fraser, and the Weekly Space Hangout. How are you all?
Great. And so where are you?
So I'm in the part of Australia that's burning right now. So if I sound short of breath, it's because we are covered in a thick cloud of bushfire smoke, which also prevents me from taking a lot of photos of space, which is what I normally do here from the easternmost point of Australia, Byron Bay.
Yeah, I think the way our two hemispheres are set up, either your place is on fire or mine is.
Yeah, it's becoming an increasing problem, I think, as we keep going forwards.
Yeah, last summer wasn't too bad. The previous summer, people could actually see the orange coloration in all of my videos for about a month because there was so much smoke from all the wildfires, and it was all going down from British Columbia all the way down to Washington and Oregon. That's awful. And I know it's been a really, really bad year for you guys. A lot of places are in danger. So is there any end in sight, or is it still as awful as it's been?
So the fires just keep going. They never go out. They're sort of under control. So most of the state is under control, except near me. They're still out of control, but they're still a way away. It's about 20 kilometers away from me now.
Now, you actually were just recently a guest on my open space. For the people who don't know who you are, who are you? What do you do?
So I run the Byron Bay Observatory. I'm really, at the end of the day, I'm just a guy who walked into a shop and bought a telescope. But I've been very enthusiastic about it, and I run my own YouTube channel teaching people about astrophotography, and I'm on Team Celestron as well because I just love the gear. And
I think, you're one of the brave people to go from amateur and to actually go and take a crack at getting your astronomy degree.
I have. For the last 2 years, I've been studying an astronomy degree, just a graduate certificate in astronomy. It's my first science degree. I've got a info tech degree, but my first science one. So I had to brush up on, I had to brush the dust off the old calculator and learn a few equations and things, which I've promptly forgotten.
Yeah.
But I'll Google them later when I need them.
So what was that like? I'm not going to lie. I've been tempted. I think we have incredibly similar backgrounds. I also have a computer science degree, and have been tempted to kind of go back and get the astronomy degree. How tough was it to get that part into your brain?
Some of the equations were challenging, but if you go for a degree that's more about science communication, it doesn't necessarily have to be, doing astrophysics or unraveling the cosmic fabric of the universe. You can just learn the broader stuff, and given your knowledge already, I think you'd probably ace that course, Fraser.
All right. Maybe I'll take a crack at it then. If someone wants to offer me an honorary degree, that'll That would save me a lot of time. And before we got into this, you wanted to talk a bit about the history of photography and astronomy. I mean, obviously you take absolutely stunning astrophotos. I highly recommend anybody goes and checks out your work. You teach people how to take pictures, but what have you learned?
Well, we take it for granted now, especially because taking photos of space has really exploded really since the late 90s. And a lot of these imaging techniques that we use, we've taken from other fields like medical imaging and microscopy, particularly in terms of stacking and averaging and calibrating frames and stuff. So the images that you see in magazines, that's not how you get them out of the telescope. They have to be processed. So in the 90s, it was something that was quite common. There was a bit of a disruption to astrophotography, a bit of a change. But we often take for granted in the really old days, there was a time when astronomy didn't even have telescopes, let alone cameras. And for people in those times, having an observatory simply meant having a room with no roof that you could sit and observe the night sky and still be able to take measurements. So in those pre-telescopic times, points of the observatory would be marked out. So you would have your degrees and arc minutes marked out across a section of the wall, or using astrolabes or things like that. And those guys, they did pretty well. And in fact, looking on their record and looking at the kind of almanacs they created in terms of star positions and stuff like that, it's really quite daunting. I certainly wouldn't have the patience and the skill to do what they did, and the mathematics to understand what was going on as well. But when we look back, these guys were Hipparchus, Tycho, Albeg, and Galileo, of course. And we look at the accuracy, and we have compared the accuracy of what they were recording with our modern day catalogs, and they're pretty close. They're not that close. They're off by a factor of arc minutes. Really, we talk about their error in terms of arc minutes. But as you know, we can't do anything with that kind of measurement, because the closest stellar parallax we can measure, which is Proxima Centauri, is sub 1 arc second. So we really need something to record those positions accurately. And that's where cameras came in. Now, the first real astrophoto was a daguerreotype by Louis Daguerre. I think it was John William Draper who successfully imaged the moon first. And back then, that was a pretty remarkable thing to do. We can take a photo of the moon with our phone these days, and it's pretty easy. But he needed to do a 20-minute exposure with that level of film sensitivity back then, a 20-minute exposure of the moon while tracking the rotation of the Earth and the position of the moon. It was hard, really hard.
I can't even imagine.
Yeah. So it was revolutionary. And taking photos of space was sort of one of the first things that people wanted to do with cameras, other than taking photos of nude people. But a few scientists got on board and realized that this was the way that they could then further their ideas about measuring stellar parallax. But before that became the focus, it was really spectra that became an interesting field of research, because they were able to measure spectra using the prism and dividing up the light and seeing where the chemistry of distant stars lay. But they were never able to actually record it before photography. So in fact, people were starting to take photos of the spectra so they could then have a catalogue with which they could then use for stellar classifications and things like that. Now, all of this was chemical, and you may know this already, but the term photography, which translates to writing with light, was actually coined by John Herschel shortly after the process was invented. So astronomers and photographers really did work in concert in those early days, and a lot of the revolutions in photography came from those revolutions in astronomy as well. despite this lack of sensitivity, it was really getting the stellar parallax. When they nailed that measurement, we could actually measure the distance of things. And Margaret and William Huggins blossomed under Harvard College Observatory's Edward Pickering, of course, and his team of female research assistants, who then were able to classify and really give us a deeper understanding of space. M42 Orion was the first nebula photo taken, of course, and for beginners today, that is the first thing we go to take a photo of the cloud in space. Unless, of course, you're in the southern hemisphere, we've got bigger stuff than that. But
just rub it in. Yeah.
But this paradigm shift with photography and astronomy was all happening at once, and it really came to a head with, of course, the Albert Einstein special theory of relativity and being able to prove what he had understood. And when we think about pre-telescopic astronomers and the way they thought about the night sky, we have to remember, before we had all these gadgets and things, it wasn't immediately intuitive to anyone to look out and see that all the stars in the sky were actually little suns. And in fact, it sort of makes sense. Like, the sun is this big glowing ball of death right in front of us, and the stars are just little pinpricks out. They really didn't make that connection intuitively at all. And so in the early days of astronomy was more of a philosophy, and science was more of a philosophy. And it was the idea of being able to intuit these things to try and unravel the truth. So a lot of the early scientific method was around Platonic reasoning and things like that. So it was a big deal to be able to move and depart from that intuitive way of thinking to be able to have technology and maths where we could unravel things. But Einstein, as you probably know, still had an intuition, and a lot of his ideas came from thought experiments as well. He had thought experiments about reference frames and, a man falling out of a building and whether he'd be able to detect it if he was in an elevator. That sort of thought experiment played into the maths he was able to use to unravel the special theory of relativity and the general theory of relativity. But none of that could be proven until the eclipse. The eclipse, what year was it? In 1919. This was the first time that one of Einstein's predictions could actually be experimentally proven. And he was able to say, look, if gravity and space-time works the way I think it does, when we take a photo of the eclipse and we can see the stars about the eclipse, those stars will have shifted. And he was right, of course, and this was an experiment that was repeatable, and it was actually repeated in Australia. So there was a follow-up expedition to take another photo of an eclipse. But it wasn't so much that he was right just about the stars moving. He was right down to the number of arc seconds they moved. He was proven right, and he was proven right again and again and again. So I think we definitely take for granted these days how much the camera and just the invention of the camera is the bedrock of what we do and what we understand now in astronomy.
Well, we talk about this idea that our eyes, as meat cameras, are dumping out the photons very quickly. We're flushing the photons from our eyes, and yet it's when you do those long exposures that you finally see all of these faint objects. And everybody always wishes they could hop on the Starship Enterprise, fly close to the Orion Nebula, and look out the window at the beautiful pictures, but it wouldn't look like that at all.
No,
you still need a camera.
That's right. And I think I look at those photos, those magazine photos of Orion, and I wonder, would I be looking at this beautiful pink sunset? But in actual fact, we are in a nebula right now. We come from a stellar nebula, and there are remnants of that nebula all around us. And if you're lucky enough on a dark enough night, you can see that zodiacal light illuminating the remains of that stellar material from which our solar system comes from. yeah, in terms of the history of photography, we then very quickly moved into digital photography, which changed everything. And NASA was really instrumental in this because it's very hard to send a film camera up to space and have it send you back developed photos of another planet or another moon. And some of the tricks that they pulled to get this done were remarkable. There were missions where images were being taken with film and developed on the spacecraft in space, and then digitally scanned line by line in order to transmit radio signals back to Earth. Again, something we take for granted these days because we have CCD and CMOS cameras. CCD was, of course, the clear winner for many, many years and still is a staple in scientific imaging. But CMOS really is catching up. And the reason for that is really because of these guys, because we all have cameras in our pocket and we keep buying them every year, every time they upgrade them. So there's a real economy of scale there for producing CMOS chips, which just keep getting better and better and better. And you would have seen that nowadays you can, with some phones, you can like point it at the sky and actually get.
I can do that with mine. Yeah, I've got enough low light on my Pixel 3A that I can take pictures of constellations and you see them in the photo.
Yeah. And this is half an improvement on the CMOS camera itself and the light sensitivity of the chip. But it's actually more of an improvement in the way companies like Apple and Google are processing their images. So when you point it at the sky and click that button, it's doing all of those things that we as astrophotographers have been doing manually for years. You know, it's registering the images so that all the stars are aligning, even though you're shaking the camera like that. It's averaging the pixels. It's removing the noise. It's gone through that whole calibration process before it even pops into your Instagram feed a little later on. So that's sort of where we're at now with cameras. And of course, the crux of this whole history of astronomy is probably the Large Synoptic Sky Survey. That is, I think, the biggest camera ever made. I don't have the stats for it here. And hopefully we'll get some great data out of it if Starlink doesn't get in the way first.
It will, and we will. Both will happen.
Yeah. Well, it's been pretty shocking, actually, to see the Starlink stuff coming through. I'm cautiously optimistic. We have processes to, it's not going to bother me so much as an astrophotographer. We're used to averaging this stuff out. You can change your stacking algorithm to remove that. But for actual science, like what happens if the one pixel we miss is the asteroid that's headed towards Earth to wipe us all out?
More cameras needed. Well, Dylan, you used up your entire interview time educating and entertaining us. So, but if people want to see more of what you're working on, your amazing pictures, your great tutorials online, where should they go?
Just Google my name, Dylan O'Donnell. I've been working very hard on my Google SEO to make sure that I'm #1 and beating all the other Dylan O'Donnells on planet Earth. So I'm pretty confident with that result.
Now, see, that's the advantage of having the info degree first, is you got the computer knowledge to then back up your astronomy skills. So, yeah. Well, Dylan, absolute pleasure. Guys. Always fun to hang out with you. I'm sure we're going to work on lots more interesting projects in the future. So everyone definitely go and check out. Now, one quick thing as well. You guys are going to be having your 2020 convention?
We do have Star Stuff 2020 lined up in Byron Bay, Australia for July 18th next year. Unfortunately, Rage Against the Machine are playing in town on the exact same day. So there's a Venn diagram of astronomers and people who listen to heavy metal, and I'm in that area of the Venn diagram.
Don't make me choose. That's my jam. All right, Dylan, thanks again, and we'll see you later.
Thanks very much. Bye-bye.
All right, let's move on to the news portion this week. Kimberly, you're on my screen. What do you got?
Hello. Well, I'm sorry. I'm going to say I'm also in the middle of that Venn diagram.
I think,
So that would have been a very difficult choice. So earlier this year, there was an interstellar comet that we detected Obviously not Oumuamua. Is it a comet? Who knows? We're never going to find out. But I am talking about Borissov, which is the second detected interstellar comet. And we were all very excited to see it. It essentially, we caught it on its way in, which means that there have been months of observations of this object. And it's actually making its closest approach to Earth in just a couple weeks, early December. It'll get, I think, 190 million miles from Earth. Super close compared to where it started. But this is, as it's been approaching, people have been imaging it more and more and more. And we got a really, really excellent, clear image of this interstellar comet to get a sense of how big it is. And it's actually, it's quite big. It's about 14 times the size of Earth when you account for the tail, which is 100,000 miles long, this tail. The nucleus itself only about a mile long, but it's been releasing all of this gas as it approaches the sun. And, you know, what I personally find remarkable about Borissov is that it looks like a comet. Right?
Even though it's come from another star system.
It's come from far away. But we saw Oumuamua. We were all like, huh, that's really weird. But there was also this sense of maybe that's just what they look like out in other solar systems. But Borissov looks chemically, physically like any comet we would see here in our solar system. And it's been a really fascinating couple months just seeing all of the different measurements and all the different observations come in. To put together this picture of what could otherwise be just a regular comet, but is fascinating because it comes from somewhere else.
But it's not just like what it looks like in a picture. Like chemically, when they looked at it spectroscopically,
yep, they've taken spectra
matches.
of the coma of the tail. It matches like 99% of the comets in our solar system, chemically speaking, in a really remarkably similar chemistry there, which like it's fascinating because you would think, you know, another solar system that was born of different ingredients. These comets are left over from when this other star, wherever it is, was born, so probably made of those same ingredients. But we look at it and it is chemically the same as what our comets are made out of.
So what do you think about, like, you know, the fact that we now have two interstellar objects that we've observed, probably both comets? I think Oumuamua is now looking more and more like a comet than an asteroid.
Yeah.
Were they happening all the time and we were just, because they look so similar to regular comets, we just didn't really recognize that's what they were?
Well, see, now the thing with Borissov is that we know from its trajectory that it could not have originated in our solar system. And we can make those same sorts of trajectory calculations for any comet that we observe. And it could just possibly be that we weren't looking, or that we happened to find these two serendipitously a year apart. And I think now that we know that they are so common that we can find them a year apart, we're going to keep looking, we're going to keep finding more. But I think one of the other remarkable things is that the fact that Borissov just looks so ordinary puts into perspective just how strange Oumuamua really was.
Yeah. I mean, like it's weird shape, it's weird, strange
shape,
outgassing, it's weird behavior.
It was tumbling.
Yeah. Well, Borissov is just behaving.
It's just like streaking in like a comet, and it's going to streak back out like a comet.
Yeah.
It's normal
with deadly cyanide gas.
Yeah.
Just
that's
like
normal.
Just like all comets.
Anyway,
yeah.
It's one of those really cool things. Like, we've been studying it for months, and we're going to still have many months to study it on its journey out of the solar system to build up an even more comprehensive picture. Though I would say I doubt we will ever figure out where exactly it came from, which solar system. There's so many unknowns.
Yeah.
With that, we're never going to figure out what star it came from. But now that we know that there's sort of like these two extremes, there's it's really plain and ordinary Borissov, and then it's the really strange and out there Oumuamua. There's these two extreme types of interstellar comets we could see, and as we start to observe more and more of them, as people go looking for them specifically, we're going to start to figure out, you know, is there Are they more like in column A or more column B?
I really like the European Space Agency's plans to try and intercept the next one of these. Their plans is to, with, I think, the aerial spacecraft, they're going to send a tiny interceptor spacecraft out to L2, and then it's just going to wait for a target. And then at some point over the next, until it runs out of fuel, they're going to be watching the sky, and when another one of these interstellar objects comes through, or some really interesting long period comet, then this thing is going to fire its thrusters and chase it down and try to provide some close-up pictures. I mean, for you as an exoplanet researcher, you're never going to get a sample of another star system, but this is pretty close.
This is pretty darn close. Yeah.
Yeah, you're not going to be able to get boots on the ground on, Peg 51, but
Peg 51 doesn't have a ground freezer.
I know, one of the others.
It has a Nobel Prize, but it doesn't have a ground.
Yeah, but to get a comet from that star system would be incredible.
Would be just fantastic. Yeah, I mean, we make all these spectroscopic measurements of stars, and we're starting to get more and more spectroscopic measurements of exoplanets and their atmospheres. And aside from the very few, less than a handful of planets that are disintegrating in such a way we can take a spectra of them eventually, we're never going to figure out what these things are actually made of. We're making so many assumptions as to the chemical compositions, how much these stars have changed over their lifetime as they burn hydrogen, what foreign material may have entered the solar systems. We make so many assumptions chemically. To actually get our hands on a chunk of material that came from one of these star systems would just be incredible.
Yeah. Oh yeah, I mean, a sample return would be just a whole other level of amazing, beyond just a pure flyby. But to actually collect a sample, land, return, that'd be the greatest.
I just have two questions. Sorry. But how many of these interstellar objects did we detected so far? And also, how quickly are they flying? Imagine if you send a probe, you have to be that crazy quick to catch them up, or maybe they are slow. I was just wondering.
So far we've only detected the two. There was the one Oumuamua, which was 2 years ago now, which I actually first heard about from Fraser on Weekly Space Hangout before it broke in the news. And then Borissov just earlier this year. Oumuamua was zipping through really, really fast, and we only caught it on its way out. Borissov, I'm not really sure if it's going faster or slower than Oumuamua, but we're catching it on the way in.
Yeah, the speed changes, right, as they orbit around the sun. So as they get closer and closer to the sun, they go faster and faster, and then they go around the sun, and then they sort of slow down again. But I think it's going to leave I forget the escape speed from the solar system, but it is on an escape velocity trajectory, so it's never coming back.
Yeah, but Nika, you make a very good point in that if we actually want to intercept one of these things, it's gonna need to have a very fast reaction time. It'll have to have a pretty strong engine thrust to try and catch up to it.
Well, there's two kinds to it, right? There's the intercept, like a flyby, and that you just need to get close and swing past it, like what New Horizons did with Pluto. But
if you actually want to match it.
Yeah, if you want to land on it and study it, then you actually have to match its velocity. And because these things are on this escape velocity, they are going really fast compared to the sun, compared to the Earth, depending on their direction. But you could, in theory, put a tiny spacecraft, like something that's just a few hundred kilograms, on top of, say, a Falcon Heavy or an SLS, and you could still chase down Oumuamua if you wanted to in about 30 or 40 years. So
why isn't Musk doing that?
Instead of sending cars.
Yeah. I mean, you definitely need the spacecraft built, needs to be ready to go. But I mean, even so, for the next probably 3, 4, 5 years, there's an interesting paper called Project Lynx, I think, and they do the math on what it would take to be able to actually catch one of these things. But the ESA's Comet Interceptor is, I think, going to be the next best thing, which is that it won't land, but it'll at least do a flyby, maybe a sample return. So
if he could even just fly through the tail,
like
and
what Stardust
collect a
did.
sample like that, that'd be pretty fantastic.
Yeah.
Any of that. I assume it's theoretically possible because they're designing it.
Yeah, and so we should see that fly in about 8 years and then be ready for its target. But it won't know what it's going to go after until the comet or the interstellar comet or long period comet comes inbound.
Well, hopefully there'll be plenty more interstellar comets where that came from.
Yes. Yeah, well, I mean, it's theorized that there are tens of thousands of them going through the solar system at any time. So it's just a matter of finding the ones that are coming close to us and not the ones that are a light year away from us, but still passing through the solar system. Nika, all right. I challenge you to explain what your topic was put into the Weekly Space Hangout. And maybe we'll workshop some titles, maybe help you come up with something a little snappier.
Yeah. I was trying to make it more explainable or easy to understand, but it is impossible because it's just the name of it. So basically, the Space 19 Plus, that is the name of the event, and it is ESA Council at ministerial level, and basically that is a 2 days event where the ministers from 22 other ESA member states, along with associate member Slovenia, and by the way, cooperating state Canada, they come together and discuss future space activities for Europe, and particularly the budgets for Europe Space Agency for the coming 3 years. So, the whole system functions as follows. So there is ESA's Director General who proposes plan for space programs to be carried out by the agency. And the member states, ministers, or the other members of the council, they commit their budgets towards the proposed programs. And basically, they are currently deciding the future of investments in Europe for space.
So is this equivalent to, say, the decadal survey that happens with NASA, or is it sort of a different, because that happens once every 10 years. This happens every 3 years for ESA?
It happens 2 to 3 years.
Yeah.
And it depends. So they change these times, but it is something similar. It's how they figure out the budgets.
It's interesting that they have a shorter time frame, because I know ESA does have some longer time frame missions as well. They have I think they have like a 2020 ESA Cosmic Visions, I think, and they also even have a 2050 one that they're considering as well.
I think they kind of agree the programs on the long term, like the general aims.
Yep.
For the programs, and then in these councils they decide on how much money do you invest in these programs, or which particular missions do you invest in.
So what were some of the projects that they decided to invest in?
Exactly. So they haven't decided yet because it's happening now. It's today and tomorrow. So if we would have recorded it just a day later, I knew exactly what they're going to invest. But there are several highlights and many interesting missions that they are focusing. Of course, they cannot focus on everything. So they have 4 main pillars, like science and exploration, application that include observation, navigation, communication, access to space, which is mainly launchers, and the new pillar, space safety and security. And each of these pillars has some missions. Yeah. For example, for science and exploration, they have missions LISA and Athena as a proposal to study gravitational waves and X-rays. They have a first mission to ice giants Uranus and Neptune. On exploration, they focus on 3 things: ISS, Moon, and Mars for the next 2 to 3 years. So for the Moon, for example, they propose to support Gateway, of course, program with the service module. And for Mars, they are proposing a sample return mission. Sample return mission, in partnership with NASA as well. So for example, for enabling and support, which is mainly focuses on access to space, so they propose to invest the money on development of new upper stage of Ariane 6 and Vega C launchers, and development of Space Rider. It's a fully reusable spaceship. Then they have this completely new pillar that they didn't have before. It's the space safety and security. And it's like, they're like smaller mission, and they have a smallest chunk of budget requested for that one. But there are like topics like study of solar flares,
right,
detecting risky asteroids, testing asteroid deflection, which is an interesting one, cleaning space, so debris removal mission. Another one was interesting. It's a quantum key distribution for secure communication of data. Then they have a new navigation mission, NAVISP, which is a navigation for deep space, for Moon, for example, and Mars missions. Then they want to invest in like 5G communication satellites, optical fiber networks, more artificial intelligence. So they're like, basically, I would say that is the highlights. There are many more, and we will see what they will decide tomorrow, basically. And the total request on all these things and many smaller one is approximately $13.9 billion.
It's interesting, like looking through the website, and this is very slick. Like you can see all of the different, it's all broken up the way you were describing, and there's videos that go along with each one of these things.
Yeah.
And yet we're still waiting to hear what their final decision and report is going to be, because it feels like this is really well put together.
Yeah, I'm still trying to understand like this whole system. It's not that easy because, like, for example, in NASA, you have one agency, basically one country. And here you have 22 member states, countries, plus European Union, plus some industries, and all can commit their budgets toward the programs, and they can participate in these programs, depending on how much they invest. And there are many country interests involved. Like, for example, French would invest totally only in launchers just because the Ariane 6 is built in France.
Right.
As an example. So,
yeah. And like a couple of those are real surprises, like a mission to the ice giants is.
Yeah. I was going to say, I am so excited to hear that is on a list somewhere.
Yeah. But of course, so exactly tomorrow we will find out whether it's gone through or not.
But it's on the list.
But it's on the list. Someone is taking this seriously.
It's under consideration, which is more than I can say for this side of the world.
Yeah. Yes, please. Well, this is great. Thanks for directing us towards this. I plan to dig through this list and see if there's some stuff that we can cover, because I really enjoy, like, NASA gets a lot of the coverage, but I really enjoy a lot of the missions that come out of ESA. I mean, for the next decade, they're going to be all over exoplanets. They've got the Cheops mission. There's the Ariel mission. There's one more. I forget. Plato, right. There's Plato. So you got 3 major missions happening over the next 10 years that are going to revolutionize exoplanets. And that's just one.
And they got Mercury mission.
Yeah, Colombo.
And they got Mars mission.
They have this asteroid mission.
And they have Hera. Is it Hera?
Yeah,
that's the asteroid deflection mission.
Yeah. Which is cool as well.
It's really cool.
Yeah. Because they wanna try to orbit it, so they can get even more. So it's
and then of course the sample return mission from Mars. Yes, please.
That's crazy, and it's just like, how are they gonna find this sample? So basically, did you talk about it in previous?
I've done a video on a Mars sample return mission in the past, and talked about how it's a collaboration between NASA and ESA, but not everybody watches my videos, so
Yeah, basically the NASA is going to gather the samples, then the ESA, the next mission, is gonna find these samples on the surface of the Mars. Then the next mission will bring it to the orbit, which is NASA's mission as well. And the next ESA's mission gonna collect it from orbit and bring it to Earth. It's just like crazy how they have to find all the samples flying around the Mars lying on the surface of the Mars.
Yeah, there's this great some sample rovers that have been put together for ESA, which are these great, very fast-moving rovers that will sort of roll across the landscape, following in the tracks of either the new rover, the ESA rover, or NASA's Mars 2020 rover, and collecting the samples that they're dropping behind them. And so with Mars 2020, it's going to drop these samples. It's going to be pooping out these samples on the ground as it goes. Rosalind Franklin, which is the ESA one, it's going to have a collection sample that it's going to be carrying with it. And so I don't know how they're going to be able to gather samples from both at the same time. I don't know if the rovers are going to meet and they're going to, at this point, collect all the samples together or something. And then it'll go and it's going to ascend in a NASA rocket. And then, as you said, an ESA mission is going to pick up the samples and bring them home to Earth, which is a great collaboration between the two groups. So it's definitely, again, like, it's so amazing to think we don't have a sample from Mars beyond the meteorites that have landed on Earth.
Yeah.
So super exciting. Please keep us updated.
Yeah, I would be happy to update you.
Alan?
There's actually
go ahead.
Sorry.
Yeah.
I just very interesting fact. They did in order to prepare these proposals, they did a survey and asked people how much money the general public is ready to pay for space programs. Yeah. And they asked 5,000 people. It's not that much, but the results were pretty impressive. So the people said they are ready to pay per year, per citizen, $287. And currently, it's just like $2 or something that is going on to space. So the public, at least in Europe, I'm sure it's the same in USA or Canada, they are ready to pay even more.
I don't know about that.
You don't know?
No.
Well, as far as our budget goes, I think individually each of us puts in like a couple cents.
Yeah, a quarter
most.
of a penny, I believe.
Yeah, maybe not even a penny into NASA's budget. And I'm pretty sure everyone who is able would be willing to give at least $1.
Yeah.
Or more. But
more.
200 is nice.
Yeah, but there was so basically people think that they're actually giving more than they are doing it now.
Yeah. All right, we're almost running out of time. Alan, what do you got?
I'm sorry.
This is the strangest idea I've heard in a while. Very cool, very science fiction. It's a team from Japan who are suggesting that it's possible to have planets forming around supermassive black holes in active galactic nuclei, which it sounds really strange at first, but the logic goes, I mean, we understand how planet formation works normally. You have your cloud of dust and gas condensing to form a protostar, and it flattens out and you get the disk and all the stuff inside condenses and you get planets. And superficially, you've got a similar structure around a black hole, right? You've got that core with the accretion disk and all heat and radiation. And then around that, material that hasn't yet reached the accretion disk. So what's been observed around supermassive black holes is that the jets and the winds and the radiation from that accretion disk tends to sculpt the rest of the material into a toroidal shape, a couple parsecs across, like a big donut, with a black hole in the middle, which has got cool material, gently turbulent. And the idea is this stuff can also then start to accumulate and collapse, form lumps, and grow and form stars, planets. Very interesting idea. I showed it to a friend of mine who works at the South African Astronomical Observatory, and she studies supermassive black holes and how they affect galactic evolution, doing a lot of simulation work. She had a couple questions. She said, this is a very interesting idea, but the main question was that they seem to be relying on the black hole needs to be fairly quiet. If it's too active, then there's going to be too much disruption in that torus, and these planets will never coalesce correctly. They'll get broken up. So that's the assumption behind the paper, is that it is a very quiet thing. But she pointed out that these black holes are not very stable. They're completely dependent on what material falls in, and they can become very active quite quickly in years or even days. So very cool idea. And I think what they've proven is that it's possible. But since it's not really testable, you're not going to be able to see these planets at that distance. I mean, it's a very long way away.
Well, fortunately, Interstellar has prepared us for the mind-bending time dilation effects you would experience being on those planets. Like, Kip Thorne worked on, famous astrophysicist Kip Thorne worked on Interstellar to help run the calculations for what kind of time dilation you would experience being on planets orbiting around a supermassive black hole. So that's already sort of been thought through.
I'm not sure that would apply to these ones though, because the distance is much greater.
Yeah, probably too far. 10 light years from a black hole. Yeah,
about that. Yeah, but what a concept! Can you imagine what it would be like? What the view must be like out there, just with the
well, you wouldn't see anything.
The lensing effect.
I would not want to live on that planet.
Yeah,
I will say I would not want to visit or live on that planet. I don't think you could. I think one of the things. Yeah, I was going to say one of the things that we're not taking into account is the radiation from the disk itself, this torus.
And even if it's quiet, you're still going to get a lot of radiation. Still has
a lot. Well, maybe not as much from the black hole as we may think, because that torus is actually, it's very thick, it's very opaque. It'll block out a lot of it, and that's what lets this material be cool enough to actually coalesce and form planets. If there was too much radiation from the black hole, the particles would just be way too hot to stick together. But what I thought was interesting as I was looking through that abstract is just like, it's a very narrow margin of being not having too much turbulence such that the things can stick together and start to form planetesimals. But just having just enough turbulence to actually like mix it up to get them to stick together. It's a very narrow range.
Yeah.
Which, I mean, narrow ranges in astronomy, you'll get it occasionally, but it seems like a long shot there.
We actually did a story. There was a great simulation that somebody had done about like the most star systems you could possibly have. Like the most populated star system would be a supermassive black hole with a bunch of black holes orbiting around it, and then stars orbiting around those black holes, and then planets orbiting around those stars. And you could actually create a giant, fairly balanced system with millions of habitable worlds all together in this gigantic environment. And it's sort of a really cool idea, sort of like, the Type 3 civilization, when they've mastered all of the resources of their galaxy, have rearranged everything, and they've done this. They've gone to the supermassive black hole at the heart of the galaxy and used that as the anchor for the rest of their civilization. So
for now, we're just getting into crazy town.
Yeah, I know. Yeah, of course. That's inevitable.
No.
But Alan, you had another black hole story to talk about as well.
Yeah, I guess I'll have to rush through this one. It was, I'm afraid I don't have any names here of, although I'm sure the names are really just telephone numbers, but the idea was a black hole detected triggering star formation in other galaxies, apart from, hundreds of thousands of light years away from itself. And the short version would be that this supermassive black hole, but almost 10 billion light years from us, has a jet extending about 1 million light years, which has created a shockwave through the interstellar intergalactic medium. And this shockwave is interacting with nearby galaxies, about 4 of them, I believe. And that has triggered star formation in those galaxies, which is quite interesting because, generally, what I understand, black holes' effects on star formation tend to be to either quench it, slow it down by heating up the gas clouds to the point where they just can't condense properly, or compressing them, increasing star formation by not more than 30% or so. And here, and that's at a range of maybe a few 10,000 light years within the galaxy. And here we're seeing this one black hole is increasing by 2 to 5 times, up to 500% increasing at a distance of 400,000 light years. It's quite something.
And this is one of those ways. I mean, it's been thought more and more that these actively feeding black holes, as they're dumping all of this material and energy out into space, and it's colliding, these jets are colliding with other galaxies are responsible for star formation. And it could be as well that as the jets are sort of blasting out of their galaxy itself and then falling back, the material's falling back into the center of the galaxy, that could also be contributing to supermassive, to star formation, and in that galaxy. And it's even sort of an ongoing disagreement about just how much of the star formation in a galaxy is responsible from this activity, from the supermassive black holes. It might very well be that we need quasars to have stars and star formation and planets and heavier elements, and a lot of that is just part of the process, as well as the other methods that can collapse star forming regions like nearby supernova or things like that. So to see this going on, to see this, this material blasting out from one whole galaxy and then a million light years away, triggering all this star formation, is just absolutely mind-bending.
Yeah, it's one of the things you learn when you first get into astronomy, is how there are these island universes and space is so big and everything's so remote, but there's a whole interaction going on between everything. Nevertheless, it's quite something.
Yeah. Well, we've reached the end of our hour. Where does the time go? Alan, you're on my screen. So where can people find out more, and what are you working on?
I am just winding up the second season of the Urban Astronomer podcast at the moment. Our last episode is dropping this coming Tuesday.
Congratulations.
No more interviews. Yeah, thank you. I'm going to take a break. I think I need it.
That's what we do with Astronomy Cast, and actually with the Weekly Space Hangout, is we take a break every summer to just replenish our energy and not have to find our way to internet every couple of days. So yeah, I highly recommend it.
Yeah, it's a good idea. And we're coming back next year. And if you want to listen, you can get the back catalog at urban-astronomer.com. There's subscribe links all over the place.
Perfect. Nika, what are you working on?
So I continue with my space events, but also in Leicester Fair, I met some interesting society, Space Cultural Society. So they do like space poetry and space philosophy and space literature. And we are planning another event maybe next year.
Wow.
So I think it would be interesting as well.
That's the kind of stuff that Paul Sutter would be into. If people wanted to find out more about you, where can they go?
Twitter, Veronica Space. I mostly post there.
Perfect. Kimberly, what do you got?
Well, let's see. I've been learning about climate change in Africa, which is not going to be a fun situation for anybody.
No.
No. And I've been learning about where OSIRIS-REx may be landing. I don't have a name for you, but you will probably be able to learn where OSIRIS-REx will be landing on asteroid Bennu at AGU's fall meeting, which is just 2 weeks away, which I've also been getting ready for.
Well, I recall CosmoQuest helping to figure out that landing spot.
I've also been speaking with our good friend Pamela Gay about how we got a really excellent map of Bennu's surface, given that she was heavily involved in that effort. So
perfect.
It's been quite interesting to learn about, and you can read about it on eos.org.
And if people want to follow you, where do they find you?
At AstroKimCartier on Twitter, and that's
awesome.
pretty much where I live.
All right, let me put everybody back in there in the gallery. There we all are. Of course, we just posted a video about in-space assembly of telescopes and sort of some interesting ideas for building 20-meter class telescopes and beyond by building them over the course of 12 launches. The next video that we've got coming out probably Friday is going to be one about exploring the atmosphere of Venus. So balloons, airships, blimps, airplanes, all kinds of stuff. So that'll be on Friday. But thank you, everyone, for joining us today for the Weekly Space Hangout. If you haven't already, definitely go and follow Dylan O'Donnell. Again, I can't stop raving about his astrophotography. He is one of the best. So definitely, if you want to learn about astrophotos, follow his material on YouTube and everywhere else. He is very prolific. Thanks to everyone watching us, everyone in the chat, all the moderators, everyone from the Weekly Space Hangout crew. We couldn't do this without you. All my co-hosts. Thanks, everybody. And we will see some of you in some combination at some point over the next unknown period of time. But you'll see me next week. Thanks, everybody.
Wait.
All right. And now there's a new button. I got to find the new button. Okay, I found it.